Hi everyone. Today we're going to be talking about separable differential equations, which is quite a mouthful and pretty annoying to write, so sometimes we call them sepi-diffy-qs, just for fun, why not? But separable, and we've seen differential equations before, if you recall. They're equations that are in the form where one side is just, the derivative of something, and an equal sign, and the other side can be whatever. It could be x plus y, it could be xy, it could be something like that. For our first example today, we'll just say that it's x, regular old x. And let's kind of revisit a topic that we saw before when we had differential equations, which was slope fields. I know it's everyone's favorite. If I have a nice little slope field going on here, well, if the derivative, which represents the slope of the tangent line, is equal to x, then that means, when x is equal to 0, the slope of the tangent line is 0. So I'll just draw in my little tangent lines here, nice and at 0. Great. If x happens to be 1, then the slope of the tangent line is 1. X is 1 right along here, so my slope of my tangent line might be 1 all the way over there. If x is negative 1, then the slope of the tangent line is negative 1 all the way over here. If x happens to be 2, then it gets a little bit steeper. Whoop. And if x is negative 2, it gets a little bit steeper, and so on. And we could probably see from this picture that, if I picked any starting point I wanted, maybe I'd say, hey, this particular function happens to hit the point, 0, 2. 0, 2? Great, so maybe that's right there. Happens to hit that point. Okay, well then I can just draw in what the curve should look like. It's got to be tangent to all of these guys. It might look like that. It might also look like that. A nice little parabola type thing. And of course it's a parabola. I mean, if the derivative is x, then the original function had to involve some kind of x squared. So this is what we did last time with differential equations. This time, now that we have some more tools, we're actually going to solve this algebraically. So if this happens to be equal to x, I want to solve this for y. Well, here's what I'll do. dy dx is the same as 1 times dy dx, so I'll just put a 1 there because it'll help us out a little bit. To get rid of a derivative, we should probably take an integral. So let me integrate both sides. And it's important that when I integrate both sides, in order to make sure I'm doing the same thing to both sides, I need to integrate with respect to the same variable on both sides. Since this is an x, I can't really integrate x with respect to anything other than x. At least I don't know how to yet. So I'll integrate with respect to x on both sides. And something pretty cool happens here on the left-hand side, where if we think about this not as dy dx one expression, but we think about it really as what it stands for, which is a rate of change of y over a rate of change of x, then these are really, really small numbers. And so this is a fraction of really small numbers, and here is a dx, which is the same small number, and so they cancel out in this nice way, and I just get the integral of 1 dy is equal to the integral of x dx. Okay, and you should feel a little uncomfortable about this because it isn't quite how it works, but for our purposes, we can think that that's how it works. And then we can just set up and integrate. The integral of 1 with respect to y is just y plus c. The integral of x with respect to x is 1/2 x squared plus c. I know you hate the plus c's coming back, but they're here. Now, here's the deal. It's really silly for us to have a constant here and another constant over here, because I could just subtract this constant from this one and write it as one new constant all over here. So that's what I'm actually going to do. I'm going to not ever put a constant with my y side, only with my x side. So y equals 1/2 x squared plus c. But I also know that there was some kind of condition here, right? I said at the beginning I want to hit the point 0, 2. So rather than drawing out this picture, maybe instead algebraically I'd use function notation. I'd say something like, by the way, y of 0 is equal to 2. And this is a nice little side note because it helps me solve for c. Remember, the plus c means I have infinitely many solutions, but giving this one condition narrows it down from infinitely many to only one that could possibly work. And so in this particular case, if y of 0 is 2, that means 2 equals 1/2 times 0 plus c, or that c equals 2. And so the actual function here has to be y equals 1/2 x squared, plus 2. Great, and there's my function. Right, this is called a separable differential equation, and we'll see why it's called that in a second, as opposed to just any old differential equation. This example, really nice. We could tell already from our slope field what the function should be, or just from our knowledge of, the derivative's x, I can probably piece together that the original function was a parabola. But what if I gave you a different function here that maybe wasn't quite as nice as you're thinking? Even though it looks super nice, it's not gonna be that nice. Let's have something like this. Let's say dy dx is equal to xy. Okay, and again, I could sketch my slope field if I want. And if I did that, I'd actually get something that, it doesn't quite look like a curve that I recognize. Maybe it kind of does, but really I can't figure it out. If you want to, go ahead and work through this on your own. I'm not going to draw the slope field here. But I am going to say, okay, here's the deal. If I tried to jump in and integrate right away, I have to integrate both sides with respect to x. This would be super bad because there's a y here. Can't integrate y with respect to x. But just like we saw in the last time, the left-hand side is going to become an integral with respect to y. And so if I can move all of my y's over here, separating the variables, then I can integrate both sides no problem. So that's what I'm going to do. Rather than having this as x times y, I'm going to rewrite this as 1 over y, dividing both sides by y, dy dx is equal to x. And now, I can integrate both sides with respect to x. This side becomes the integral of 1 over y dy, and this side just becomes 1/2 x squared plus c, just like we saw last time. And the integral of 1 over y is just natural log of y. And, we want to solve for y, though, so how do I solve this for y? Well, we remember that to get rid of natural log, right, this is really log base e equals this. So to rewrite it, it means e to this power equals y. So that means y has to be e to the power of 1/2 x squared plus c. And, this is kind of weird because constant in an exponent, that's a bit odd. So we remember that when you're adding two exponents, what it really means is, this is actually e to the 1/2 x squared times e to the power of c. And more commonly, since e is a constant and c is a constant, we can write this as just one big constant, or the capital letter C, which looks indistinguishable from my lowercase c. But know that it is the capital letter C. So here's the solution to this differential equation. And let's say you don't believe me. Let's say, Mr. Sacchetti, this is stupid. There's no way that that equals that. Well, fortunately, I know derivatives, and I know them pretty well because I've been doing them for a while. I can check. I can take the derivative of both sides here, and that would give me dy dx is just equal to, let's see, e to the 1/2 x squared times the derivative of this exponent, which is x. And then, times c because constant multiple rule. Well, that's cool. That doesn't quite look like that. But I notice that y equals this, so I can rewrite these two terms as y. Oh, great. Everything rules. Okay, so, good. Separable differential equations, as they're called, because we can separate the variables. Here's what I'm going to do right now. I'm going to put up another separable differential equation. And once I do, I'm going to ask that you pause the video and try this one on your own. And then I'm going to do it out here for you here, so that if you're not feeling totally confident about how it went, you'll have a solution. So why don't you take a look at this particular differential equation. dy dx is equal to 6y squared x. Here it is. Take a minute, pause the video, try it out on your own, see how it goes. But I'm going to go ahead and solve this right now. Hopefully you've already tried it, and everything I'm about to do will match. Need to move the y's over here, so I'll do that. 1 over y squared dy dx is equal to 6x. I'll integrate both with respect to x. This integral just becomes 1 over y squared dy. This is y to the negative second power, so I use the power rule, add 1 to the power, divide by that new power. I get negative y to the negative first, and that's got to be equal to 3x squared plus c. And, well, this is weird, right? Because I want to solve this for y. Y to the negative first, that's the same as negative 1 over y here. To solve this for y, I'll cross multiply. Right? This is over 1. Multiply by y. Negative 1 is equal to 3x squared plus c times y. And then I'll just divide by this term here to solve for y. And I'll get y equals negative 1 over 3x squared plus c. And this will be the solution to my separable differential equation. Let's throw in a condition there. Let's say, oh, by the way, I want the very specific equation where y of 1 is equal to 1/3. Okay, sure. So I can figure this out, no problem. Well, y of 1 is 1/3. That means when x is 1, y should be 1/3. So to myself, I'll just say, okay, great. Negative 1 over 3 times 1 squared plus c had better equal 1 over 3. Well, this is negative 1 over 3 plus c equals 1/3. And we can cross multiply and solve for c. C is negative 6. Great. So my very specific solution in this case is y equals negative 1 over 3x squared minus 6. And there it is. Awesome. There is one other thing that tends to come up when we're dealing with differential equations. And it's not quite how to solve them or how to get the original equation. It's more of a, hey, I'm going to describe a scenario to you, and then can you tell me the differential equation that I'm describing? So let's do one example of this type of problem. If you want to see another one, the 2012 AP exam had a free response question about the weight of a baby bird that was a differential equation, which was pretty cool. Cool problem. For right now, let's do this problem. Let's say the rate of change of a population is proportional to the population. First, we should pause and say, does this make sense? Well, if a population increases, the rate of change of that population will probably also increase. Because if people are having babies and then there are more people, then more people are having babies and there are even more people. So this kind of makes some sense as a concept here. Rate of change of a population. Rate of change is a term that we've seen so many times. So hopefully by now we recognize it, meaning derivative. So if I'm going to say let P be the population, then dP dt, I'm going to call it dt because, well, this is rate of change. I'm assuming it's changing over time. is going to be the rate of change of the population. So far, that seems okay. If these two quantities are proportional to each other, that means that dp dt is equal to some constant times p. That's all that means. And if you wanted to find an equation to model this population, we could do that too. In this case, it's a little different, but it's the same type of setup. P is the variable that we had been calling y, and t is the variable that we had been calling x. So we're still going to separate this just like we did before, and it shouldn't be too bad. We'll get 1 over p dp dt is equal to k. The trick here is k is a constant, it's not a variable, so keep that in mind. When we integrate both sides, we'll integrate with respect to t, because that's our x variable, as it were. This gives us ln p, and this gives us tk plus c. And so this is almost exactly like the equation that we saw just a bit ago. And the solution to this equation, right? This means e to this power is equal to p. So that just means here p is again equal to some capital C times e to the kt. And just like last time, we could check, well, if I took the derivative of this, I would get this exact thing again, except times k. And that's exactly what this differential equation is saying here. So, these types of problems can be a little tricky. There was a problem like this on the practice multiple choice that we took a little while ago. So going back to that and checking over that answer might be something helpful for you, especially since we'll have this other multiple choice coming up very soon. So that's all for differential equations today. Thanks for watching, and best of luck with the classwork.